Layers and softmax. We're going to look at our first example of a layer by generalizing logistic regression. First, though, we're going to look at maximum entropy models. Maximum entropy models are closely related to maximum likelihood and many other important ideas. We begin by looking at models for discrete variables. If we have a sample space, a discrete one, S equals O1 up to OM, that's our outcomes. A model is just a distribution for a variable y associated with S. So for example, if we say P of x equals 1 over m for all x equals 1 up to m, then that's the uniform distribution. Another example of a distribution is we could let P of 1 be 1. In other words, the outcome O1 is certain. P2 equals P3 all the way up to P of m equals 0. Now we're using y here because it represents the class variable, and models are going to predict the class of an observation. Now let's combine models with data. Suppose we have n trials producing outcomes little y1, little y2 up to little y capital N. And the outcomes here, again, we're thinking of as class predictions. We're going to suppose that each trial is independent of every other, and this is an issue of veracity. So big data must also be good data. Often that means that the big data has to be collected so that we can make this each trial independent assumption, or assumption similar to that, which will also be necessary. And maintaining consistency by using the same measurements and features and scales throughout the entire collection of the data. Just anecdotally, I once had a client. He had about 10 million data points, and he didn't want me to know what, or better, who had missing data. And so therefore he replaced all the missing values with zeros, even though there are already zeros in the data. It made it impossible to impute missing values, and so we just got nonsense out of this until we negotiated a process where he learned how to impute missing values before giving me the data. Again, he had something about not wanting to know who the agents were in the data set generating process that were actually producing missing data. So there also is going to be a true distribution, piece of true, that we don't know, but that's going to be what's responsible for the data that we've collected. That leads to the empirical distribution. So you've got your n trials producing outcomes little y1, little y2 up to little y sub n. We let capital Y sub I be the variable or class predictor for the ith trial. The y sub I are independently identically distributed, and C sub n of x is a count of outcome O sub x. It's how many times the outcome O sub x occurs in n trials. So the empirical distribution is just P tilde sub capital N of x, which is Cn of x over n. It's pretty easy to show that the best approximation for the true distribution is the empirical distribution if n is very large. Next, we're going to look at that in just a moment. And this is also if we ignore all the features, structures, constraints. So if P true is producing results without any kind of constraints due to the features or structures, then the empirical distribution is the best. Now let's use data to find the best model. And we're going to do that using a parameterized family of models. This is a collection of distributions, P of x semicolon w, where w equals w0 up to wk are parameters. And this is a very important idea because a parameterized family is often better than pure or empirical distributions, at incorporating the nature and structure of the data and explaining what's going on. So things like linearly separable complex networks, feature selection, this usually comes from looking at parameterized families of models rather than from empirical or trying to search for this very complicated pure distribution. So a natural question is going to be, which model in the family, which values of the parameters, is most likely to cause the data? Okay. Now, we're given the data and we're given a family of models, and what we want to find is the best model, in the sense of the best model is the one that was the most likely to produce the data that we have. And that means finding the values of the parameters such that P of x semicolon W is most likely to produce that data. How do we do this? Well, we know about KL divergence. And so if we look at the KL divergence between the family and the true, then if it's close to 0, if it's equal to 0, these two are identical. If it's close to 0, then we get a good approximation of P true with this member of the family. So we're going to let Y sub W be distributed as P of x semicolon W, and Y sub true distributed as the true distribution. And we'll let bold W star denote the parameters that lead to this maximum. Remember also, probability distributions are dimensionless. Densities, which are inside of integrals when you're looking at continuous probability, densities have units, but distributions do not. So let's look at first a capital Y sub tilde variable distributed as P sub n tilde of x, the empirical distribution for large n. Then the empirical distribution approaches the true distribution as capital N goes to infinity. That's the law of large numbers. And that implies that the Kullback-Leibler divergence, which is negative, x equals 1 up to n, P sub true of x, log of P sub true of x up to P sub n tilde of x, that goes to 0 because we get P sub n approaching P true, which means we're approaching the log of 1, and the log of 1 is 0. Now, we want to look at, for large n, finding the best parameters, which means minimizing the KL divergence. So let's look at the KL divergence between the true distribution and the parameterized family. That's the sum, x equals 1 to capital M, P sub true of x times the natural log of P of x semicolon W over P sub true of x. And we can split the logarithm and get two sums, x equals 1 to M P sub true log P sub true minus the sum x equals 1 to M P sub true log P of x semicolon W. And notice that the first term is constant because it's in terms of P sub true, and that's not going to change as the values of the parameters change. So in order to minimize the KL divergence, we need to maximize the term that's being subtracted, and the n here is very large, so we actually want to maximize x equals 1 to m of P sub capital N tilde, the empirical distribution of x, the log of P of x semicolon W in the family. And that's because as n goes to infinity, we get that last term, the sum x equals 1 to m P sub true times the log of P sub x semicolon W. And this leads to what's called the maximum likelihood principle. So for a given data set, for a variable y sub w with distribution P of x semicolon W, the log likelihood function is ln of L equals the sum x equals 1 to capital M P sub n tilde of x, the empirical distribution, times the natural log of P of x semicolon W. And so the model P of x semicolon W star that maximizes the log likelihood function is the one that's closest in some sense to P sub true as n goes to infinity, and closest in the terms of the KL divergence. And all of this, by the way, is in units of nats, since we're using natural logarithm. Now let's do more with this log likelihood function. Let's start out by defining the characteristic function of a condition to be 1 if the condition is true and 0 if the condition is false. So we look at the log likelihood function. The empirical distribution is C sub n of x over capital N, which the 1 over capital N can be factored out because it doesn't depend on x. And the C sub n of x can be written as the chi, the characteristic function, of y sub I equals outcome O sub x times the natural log of P of x semicolon W. So this gives us what we actually want to maximize. So we can also notice that the natural log of L is 1 over n times the sum x equals 1 to capital M of the log of P of x semicolon W to the C sub n of x. And now we can take the sum of the logs and write it as the log of a product. So we get 1 over n, the natural log of the product, little x equals 1 up to capital M, P of x semicolon W, to the C sub n of x power. And that gives us our likelihood itself is all to the power 1 over n, the product, x equals 1 to m, P of x semicolon W to the C sub n of x. Now, the 1 over n here doesn't really do anything. It would be perfectly fine to just drop the 1 over n. So, let's talk about determining the actual form of the models. The maximum likelihood comes from minimizing d sub y true with y sub w. But the KL divergence is a divergence. It's not a distance. And in particular, it's not symmetric. So dy sub true with y sub w is not the same as d of y sub w with y sub true. And there's not a simple connection between them. So that means we would get a different set of parameters if we had started instead with dy sub w with y sub true. So instead of trying to get parameters, let's step back and use dy with y true to just suggest what kind of models we actually get, what the general form is going to be. So we're looking at y as a distribution, or y as a variable with distribution p of x, where p of x now is going to be a vector of variables. So p of x you should think of as p1 up to p sub x up to p sub m, where each one of these is a variable in m-dimensional space. Now, what I'm about to show you is a little hand-wavy. There's a theorem that we need, but we won't get to it until Operations Research 2, the Karush-Kuhn-Tucker theorem. And we're going to get essentially the same result, but it's not going to be completely rigorous because I don't have that theorem from OR2. So we are going to simply let f of p1 up to pm, the function of these m variables, be this KL divergence. So let's write out what it looks like, and we're going to use indexes. So the f is going to be the negative sum j equals 1 to m, p sub j, the natural log of p true of j over p sub j. And that's going to be the sum j equals 1 to m of p sub j log p sub j minus the sum j equals 1 to m p sub j log p true of j. Now let's take the derivative. And the derivative of f with respect to the variable p sub x, again we're thinking of p1 to pm as a set of m variables. That's the derivative with respect to p sub x of this sum j equals 1 to m p sub j log p sub j, minus the derivative of the sum p sub j log p sub true of j. Now the derivative of the first is going to be everything from j equals 1 to m that's not x is going to go to 0, and where you have x, you're going to get the log of p sub x from the p sub x log p sub x term, minus p sub x times 1 over p sub x. So that log of p sub x minus p sub x times 1 over p sub x is the derivative of p sub x log p sub x. And the derivative of the sum p sub j log p sub true j is 0 except where j is equal to x, and so therefore we get simply the natural log of p sub true of x. And notice that this final two terms does not depend on p sub x. So we're going to rewrite this negative 1 minus the natural log p true of x as a term depending on x, and notice dependence on x is different than the dependence on the variable p sub x. So this phi of x is going to give us our dependence on the index x, minus the natural log of c is going to give us our constant. We use the minus natural log of c so that the c becomes a multiplier, as you'll see in just a minute. So the derivative with respect to p sub x is log of p sub x minus phi of x minus the natural log of c. And to be a minimum, we have to have that the derivative is equal to 0 for all p sub x. So setting it equal to 0 means that the log of p sub x minus the phi of x minus the natural log of c is 0, and therefore p sub x is c e to the phi of x. However, the p sub x's have to sum to 1. And so if we take the sum p sub x is equal to 1, then that's c times the sum x equals 1 to capital M e to the phi sub x power is equal to 1. And so now we have our general form for the p of x's, and now I'm going to write, instead of p sub x, I'm going to go back to writing p of x again. And p of x is e to the phi of x over e to the phi of 1 plus all the way up to e to the phi of m. Now, we're going to put that to work by looking at softmax and layers. Maximum entropy leading to softmax and layers. So softmax is logistic regression with multiple classes. How do we extend to multiple classes? We actually have already seen that because we ended the previous with the general form of a p sub x in terms of these phi sub x's. So if classes are subsets of mutually disjoint convex sets, then linearly separable tools apply. And just to note that the sklearn implements multiple classes. So for k equals 1 up to capital M classes, we're going to let the phi of k be w sub k dot x. And this means that our phi of k is a set of linear functions of the features, because our x now, our bold x, is going to be the features, like gender and age and stuff like that. So we'll let w sub k be a vector of w sub k0, w sub k1 up to w sub kn, where k equals 0 up to m minus 1. And that means, using our general form, we're going to have p sub k of x is equal to e to the w sub k times x over e to the w0 times x plus up to e to the w sub k times x plus e to the w sub m minus 1 times x. And then we'll determine thresholds t sub k, k equals 0 up to m minus 1, such that if p sub k of x is greater than t sub k, then we'll say that x is predicted to be in class k. Now there's a technicality here. There's one too many w sub k's because this probabilities all sum up to be 1. And the way we can get around that is we can just arbitrarily let one of them be equal to 0. So w sub 0 equals 0. So there's only m minus 1 independent probabilities. So we let W0 equal 0. And then P sub 0 of x is going to be 1 over 1 plus the sum of e to the w1 of x all the way up to e to the w m minus 1 times x. And that's equal to 1 over 1 plus the sum k equals 1 to m minus 1 e to the w sub kx. For the other k equals 1 up to m minus 1, p sub k of x is e to the w sub k dot x over 1 plus the sum j equals 1 up to capital M minus 1 e to the w sub j dot x. So what we've done here is simply let one of the vectors be 0, and so we get e to the 0, and then everything else is e to a dot product of a w sub j dot x. And doing that, notice that p sub k of x over p sub 0x is e to the w sub k times x over 1. That's just e to the w sub k dot product with x. So what we have is the probability that y equals k over the probability that y equals 0 is e to the w sub k of x, w sub k dot x. And the natural log of the probability of y equals k over probability of y equals 0 is wk dot x, which is linear. So Softmax is multinomial logistic regression. What we're doing is we're assuming that the log of relative odds is linear. What are odds and log odds? Well, we've seen those previously. But in order to get a better feel for it, let's look at logistic regression again with multiple classes. And notice that we can generalize even further so that we could put a beta sub k times w sub k dot x. And this is really just for convenience, because if the w sub k is a parameter, then the beta sub k w sub k is also just a parameter. But it allows us to see that if beta sub k is very large, then either e to the beta sub k w sub k dot x is approximately 1, or e to the beta sub k w sub k dot x is approximately 0, depending on whether w sub k dot x is positive or negative. So that means that our probabilities are either 0 or approximately 1 over kappa, where kappa is the number of times that e to the beta sub k w sub k dot x is approximately 1. So what does this mean? Well, if k is large, then 1 over k is approximately 0. So even though we can use logistic regression for multiple classes, this shows us that as the number of classes becomes very large, it really becomes sort of pointless, because all the probabilities become very close to 0. Now let's suppose we look at an example with m equals 2 classes. Then p1 of x is e to the w1 dot x over e to the w0 dot x plus e to the w1 dot x. And we can multiply by e to the negative w1 dot x on the top and the bottom. And we get 1 over 1 plus e to the w0 minus w1 dot x. Now, w0 minus w1 is one parameter vector, so there are too many w sub k's. So again, we'll let w sub 0 be equal to 0. So p1 of x is 1 over 1 plus e to the negative w1 dot x. And that's just the same activation function that we saw with logistic regression. And then we can say that if p1 of x is greater than some threshold t1, then x will be predicted as class 1. But what about class 0? Well, if p1 of x is less than t1, then that's the same as 1 minus p1 of x greater than 1 minus t1. So 1 minus p1 of x is 1 minus the quantity 1 over 1 plus e to the negative w1 times dot x, and simplifying the fraction, we get e to the negative w1 dot x over 1 plus e to the negative w1 dot x. And simplifying that further, we get 1 over 1 plus e to the w1 dot x. And notice that that is actually the form e to the w0 dot x over e to the w0 dot x plus e to the w1 dot x. So we've just shown that 1 minus p1 of x is equal to our 0 class form. Again, recalling that w0 is 0. And so 1 minus p1 is the p0 form. And we could let t0 be 1 minus t1, and that would give us our threshold in this case. Now, the softmax, if k is equal to 0 or 1, we get the probability that y equals 0 plus probability that y equals 1. That sum is 1. So the natural log of the probability y equals 1 over the probability y equals 0 is equal to w dot x, which implies that the natural log of the probability y equals 1 over 1 minus the probability y equals 1 is equal to w1 dot x. So if we let p be equal to the probability at y equals 1, then we get the natural log of p over 1 minus p is equal to w1 dot x. So what we've done here is shown that softmax generalizes odds and log odds and extends logistic regression to multiple classes. Moreover, softmax is a layer. So what we need to think is in terms of the features forming a set of variables x1 up to xn, like gender, age, income, those sorts of features. And then we have the functions x going to e to the w0x over e to the w0 dot x plus up to e to the w sub k minus 1 dot x. And then the last cell, e to the w sub k minus 1 dot x. And then we have the predictions, the y0 to the yk minus 1. And of course, there's only k minus 1 independent of these. But we often envision these as being a layer. And by a layer, we mean we think of the x's as inputs to the softmax layer, which then have outputs, which are the y0 to yk minus 1. And we'll see more layers as we go along. Softmax is one type of layer. For two classes, it's just logistic regression. Again, if we got k classes, there's only k minus 1 independent predictions. And so sometimes we'll just take a 0 class, and so if we've got k classes, we'll just create a 0 class, which is all the things that are not in one of the k classes. Softmax is a linear classifier. Talk more about that in the next module. And a bonus. Since we're here, let's look at the Akaike information criterion, because we're right here where we can understand it. Now again, what I'm going to do is going to be sketchy and hand wavy, but it should make sense. I just want to introduce this idea to you. It won't be rigorous, but it should be useful, and we're right here where we can actually play with it. So what we're going to do is we're going to let W star be the maximum likelihood estimated parameters. And we're going to expand the log likelihood in a series. And I don't have it exactly the way that it should be done. Actually, we should define a concept of one variable and two variables. One parameter, two parameters, three parameters, so on and so forth. But the key here is that you expand in a series. And the linear term is 0 at W star because we have a maximum likelihood estimate. And so what that means is that the maximum likelihood estimate that we get at W star is actually a biased predictor. And it's biased by the number of parameters that are in the W vector itself. And what we can do is we could exponentiate, get probabilities, we get the Hessian term becomes something like a chi-square. And what we find out is that this W star equals W0 star up to W sub k star has k degrees of freedom. Now, this was only quick and sketchy, but what it implies is that if we replace the Hessian term by k, doing a lot of work with the chi-square distribution make this rigorous, then we can let the natural log of L star denote the maximum log likelihood. Then the AIC criterion is 2k minus 2 natural log of L star. And what does this actually mean? Well, the 2k here is a penalty for the bias that we get in the series expansion of the log likelihood. So the AIC is information that's lost using this candidate model as a model of the true model. So therefore, given two models, the preferred model is the one with the smaller AIC, the less information difference with the true model. So how would you actually use this to compare two models? Well, we're measuring the AIC. Actually, the negative AIC over 2 is measured in nats. So the exponential to the AIC is a probability, or better probably call it a likelihood. So if we have a set of models, 1 to r, and we compute the AIC for each one of those, then the AIC sub min is the AIC, smallest AIC. Then we interpret the e to the AIC min over 2 over e to the AIC j over 2 as the relative likelihood, sort of like the odds ratio. How much more likely we are to lose information from the jth model than from the min model. There's also an AIC sub little c that corrects for sample size. Now, this has been kind of hand-wavy, so let me reinforce it with an example. Let's suppose I take data and let's suppose I take a linear function, y equals 2x plus 3, and I add some Gaussian noise. So I've got some samples, the 25 values of x, then I get 25 values of y corresponding as 2x plus 3 plus the Gaussian noise. Let's look at two models that we could fit to this. We could fit a linear model, y equals mx plus b, or a quadratic, y equals ax squared plus mx plus b. Here's the Python code that you actually use to do that. So you can see that I just simply generated the y equals 2x plus 3 plus the Gaussian noise. Then I did some pre-processing using the sklearn pre-processing polynomial features to get the x coordinates for polynomial fits of sizes 1 and degree 1 and degree 2. Then I incorporated the API from the stats models, and then I used ordinary least squares and got a linear fit, and this is the L results, the linear results, and then found its summary. And same thing, I did a quadratic regression, which was once again in ordinary least squares, and I got Q results and also had the Q results dot summary and the AIC. And then I got the parameters using the L results dot params and the Q results dot params. Now here are the results. I got the linear model from L params is y equals 2.068x plus 3.036 as a prediction of the best fit for y equals 2x plus 3 plus Gaussian noise. And you can see it's respectable. The quadratic model was y equals negative 0.741x squared plus 2.809x plus 2.918. So you can see there that the slope 2.809 is quite significantly different than the slope 2.068x for the linear model. So which is the better model? Which is the better model? Well, let's look at the linear example first. So we've got the mean standard error was 9.654, and the r squared, which ideally is equal to 1, and close to 1 is better than far from 1. So the r squared for the linear is 0.873. And notice the quadratic, the mean squared error is 4.872, and the r squared is 0.881. So in this sense, the quadratic has better mean squared error and r squared. Why? It has more parameters. So if it has the parameters a, m, and b, then the a equals 0 special case gives you the linear fit. And so the more parameters you have, the better fit you have, because you can do no worse than what you would do with the linear fit, and certainly can do better, as we see here. But the real question is, which is the better model? So just eyeball test and looking at the simulation itself, we really want to say the linear model is the better model. Its parameters are closer to what we used originally, and it's linear, whereas it's we didn't start out with a quadratic. We started out with a linear. Now let's look at the linear. The AIC is 2.977, but for the quadratic, the AIC is 3.341. So even though the quadratic is a better fit, the linear is a better model. Why? Smaller AIC means better model. So just a quick little postscript showing you how to use the AIC. It's very handy for comparing one model to another and choosing which is the better model.